When calculating the heat from a reaction, it's important to understand that the heat depends on the quantity of substance. For example, this is the reaction for the combustion of methane, CH4. The enthalpy of this reaction is negative 882 kilojoules, which means that 882 kilojoules are produced when this reaction occurs. But it's not just for any amount of methane. It's only for a certain quantity. If I have more methane, I should get more heat. And so 882 correlates to the amount that's actually written in the equation. In the equation, we can use the coefficients in order to determine how much this correlates to. And so we can actually write that there's negative 882 kilojoules for every 1 mole of CH4 that is combusted. Alternatively, we can actually write this for any of the reactants or products in this reaction, which means that there's also negative 882 kilojoules for every 2 moles of oxygen. We could do the same thing for carbon dioxide, and that would be for 1 mole of carbon dioxide, or for water, it would be for 2 moles of water. By writing this relationship, we can use this to figure out how much heat is actually produced. For example, if I combust 2 moles of methane, I expect that I'm not going to get 882 kilojoules, because I get 882 kilojoules for 1 mole of methane. 2 moles of methane should yield more. And so we can use this ratio as a relationship to actually solve for the amount that we actually produce. And so by canceling units, we could see that we should put 1 mole of methane on the bottom, and we can write the negative 882 kilojoules on the top. Crossing things out, we could see that we're going to form negative 1764 kilojoules by burning 2 moles of methane. This overall equation can be summarized as the moles times the enthalpy will be equal to the heat that I'm actually producing. And so it's really important to account for the amount of substance that's actually occurring. Let's try another example. Here we have the reaction for the formation of methane, CH4. This has an enthalpy of negative 74.8 kilojoules. Once again, I can correlate the enthalpy to the quantities of substance in the equation. So there's negative 74.8 kilojoules per 1 mole of carbon, negative 74.8 kilojoules per 2 moles of hydrogen, or negative 74.8 kilojoules per 1 mole of methane. You can write any of these. And so if I had 6 moles of hydrogen that were reacted in excess carbon, I could figure out the amount of heat that was produced. I could use either of these relationships. In this case, it makes sense that I use the middle one that involves hydrogen so I can cancel units. And so I can multiply 6 moles of hydrogen by negative 74.8 kilojoules for every 2 moles of hydrogen. When I cross out my units, I could see that I'm going to get negative 224 kilojoules as my answer. And so this means that 224 kilojoules of heat were produced by reacting 6 moles of hydrogen in this reaction. We also could have done this with a little bit more stoichiometry. We could have also done 6 moles of hydrogen, converting to methane, saying that there's 1 mole of methane for every 2 moles of hydrogen. And then we could have used actually any of the other relationships. And so I can use the third molar ratio as well, saying negative 74.8 kilojoules per 1 mole of methane. Since all of my units cancel, you'll notice I actually get the same exact answer for this reaction. And so you can use any of the molar ratios that you get from the equation to solve for the heat produced by a reaction.